So I'll just give you a quick overview of the talk. So I'm just going to introduce continuous gravitational waves and some of the problems associated with that and how we search for those. Then I'll go more specifically into one of those searches entitled SOAP. And I'll talk about some of the details about how that works and why it's useful. Then the further two sections, one of them being our use of convolutional neural networks to improve this search as an addition, and how we use machine learning as well for parameter estimation of these. So that's sort of the quick overview of this talk. So what are we searching for? Right. So generally searches for gravitational waves, we can split into four broad categories. On the left side here is compact binary coalescent signals and burst signals, which are short duration. CBCs being well-modeled sources, such as binary black holes or binary neutron stars. Burst signals being sort of an unmodeled search, where they can be from supernova or other sources. On the longer duration side, you have continuous waves and stochastic signals, where stochastic signals are unmodeled and continuous waves are well-modeled signals in general that we have, but a long duration. And that's what we're interested for this particular talk. So where do these come from? Quick play on that. So continuous waves are like the key source for these are thought to be rapidly rotating neutron stars. So if these neutron stars have some asymmetry in their mass distribution around the rotation axis, they can emit gravitational waves. And so there's various different mechanisms which can cause this, including if it's in a binary system with a star and accretes material down through its magnetic field, it can heat up a spot and that can change density, etc. There's various different mechanisms that can hold up some sort of mountain, is how it's thought. So it's a relatively simple signal, really, that we're searching for. It's just it's a sinusoid where as gravitational waves are emitted, the idea is that it will lose energy and its rotation rate will decrease. It will spin down. So it's quite a simple signal. It's just a slowly decreasing frequency sinusoid. But it's not quite just that simple, because obviously we're detecting that with a detector on the Earth. So we have this spin down. So in the top right panel of this plot, you can see sort of the slow spin down over time. Say that's over 6 years, I think, that plot. And that's one mechanism. But you have this oscillation as well, and that's due to the orbit of the Earth around the sun. So you get this yearly oscillation, and you also get a rotation of the Earth. So that's a smaller oscillation on that also. And this just adds to the complexity of the search, really. So what's next? So how do we actually search for these? So it's still a relatively simple signal, right? It's just a Doppler modulated sinusoid, really. And there's a few different ways we search for these and a few different categories, which we set depending on basically what we know about the source already. So if you observe a neutron star, there's not only gravitational waves, although we haven't seen them yet. That's not the only way to observe these, right? We observe pulsars quite often in radio and X-ray and other things, mostly radio, and we can see it where it is on the sky, for example, and we can observe its frequency and frequency derivative. And if we know all of that information before we do our search, we can we do what is a targeted search. We target it towards that source using what we know about it beforehand. Directed searches are somewhat similar in that we only know the sky position, but we don't know its frequency or frequency derivative, so we have to search over all of that. And then finally, there's all sky searches, where we know nothing prior to the search, and we just search everywhere over the entire parameter space for a signal. And that's where the focus of this talk is, on all sky searches. So we're just looking for any neutron star which we can observe, or any long duration signal, really. It doesn't have to be a neutron star. So how are these done? So traditionally, these targeted searches where we know exactly where the source is and what frequency it's at, we can generate sort of a filter bank for these. So we can do matched filtering, right? So this is still a huge amount of data, right? So this is over an entire year or an entire observing run, which is approximately a year. You can do this search and you can generate templates around the frequency you think it is, or around where the sky position is, and you can just correlate that with the data to try and search for it, right? So in the top here is an example. Obviously, this amplitude is way higher than we expect, and it's only a short duration, but that's what a sort of matched filter, a coherent matched filter would be like. Now, if we wanted to do this for an all-sky search, we'd have to generate templates for the entire sky and the entire frequency. And And we have really good resolution on the sky with these searches because we essentially, because we observe for a year, we orbit the sun once. So it's like, well, it's almost like having a telescope the aperture of of 1 AU really. So if we wanted to place templates across the sky so that we could sufficiently search that space, I think we'd need around order of like 10 to the 14 templates to search over. And that's not accounting for all the templates we need in frequency, which we have a high resolution because we observe for, again, over a year. And so searches, doing a match filter for this kind of search is not feasible at the moment with the current computing powers that we have. So what we do instead is we can break up that data into small chunks, right? That's what this plot on the bottom is. It's the same piece of data. We just broken it up into chunks. And then we can analyze each of these segments sort of coherently with a filter or some other technique independently, and then combine those results afterwards. And that can just, whilst we lose some sensitivity, it makes it possible to do the search ultimately. So what are some of those techniques that we use? So in the all sky searches that we have at the minute, there is a couple of different techniques. These are just some of them, by the way. There are others. One called a time domain F statistic, and that's basically doing a matched filter where you take a waveform which has some spin down on it. You compare it to a chunk of data. They pick somewhere of ordered days, like 1 to 6 days, I think, at the moment, and do that on lots of segments across the year. And then they find coincidence between these segments, and that works quite well. And that's quite the longer coherence time generally. The longer the time segments are, the more sensitive you are, is the general rule. Other searches then just use sets of FFTs, right? So you can just take a bunch of FFTs of the data, and that's what sort of your coherent search in a way. And then you can look at the frequency bins in that and try and identify a signal. So there's these things called a Huff search, use a Huff transform. I won't explain necessarily what that is, but basically you can go from your time frequency space into parameter space. So there's two variants of this, one where you fix the frequency of your signal and you can generate this Huff transform space on the sky parameters, and you can do it the other way around for a fixed sky position. You can generate that in the frequency and frequency derivative space. And that's another quite a fast search for continuous waves on the whole sky. The final one here is SOAP, which is what I'll be talking about mostly now, which is takes a somewhat different approach to the rest of these, where we don't assume much of a model and we just intend it to be really, really fast so we can identify candidates for other people to look into further. So SOAP, what is SOAP? It stands for snakes on a plane, if you wondered, which because we look for snake-like things in the time frequency plane. But it's based on a Viterbi algorithm, something called the Viterbi algorithm, which is quite widely used in various other fields. But it identifies a track through here, which gives you the maximum sum of some statistic. That's what we say there. But basically, you can imagine that the premise of this search is that this is a time frequency, like something we'd expect out of LIGO, by the way, this plot. So a very clean LIGO without any instrumental artifacts. It's a 0.1 hertz wide band, and it's for like just over a year or a bit longer than a year by the look of it. And this is the power spectrum from a set of FFTs. And you can imagine if you found every possible track going from left to right in this plot, you have some constraint that it can't jump like 10 frequency bins or something, because that's not very physical. But if you looked at every possible track, you'd imagine that if there was a signal in there, the track that followed that signal, i.e. the lower one in this plot, would give you a much higher sum of FFT power along this track. And so you could turn that around and say, if I looked at every possible track through here, one which gave me the highest sum is most likely to be from an astrophysical signal. And that's all of the basis of this search. And so it's relatively simple, really. But what we use is the Viterbi algorithm, which can do this very efficiently. So how does that work? Okay, so if you want to search through every possible track through a spectrogram, it would take approximately the number of frequency bins times 3 to the power of the number of time bins, assuming we're only allowed it to change by 1 frequency bin each time. There's 3 possible choices each time step. Now the Viterbi algorithm does this in 3 times n times n, the number of frequency bins times the number of time bins. So it's substantially quicker. But how does it do that? Okay, so on the left here, you can see an example of a small spectrogram, if you like, and all those numbers refer to the power spectrum values. And on the right is sort of an empty grid that you create for the Viterbi algorithm to fill up with some statistic which you define. So the first cell just gets filled with the data because there's no information about where a track could go or could be. and the little C's refer to center. And there'll be a U, a D, and a C here, which refers to whether it comes from a bin up, down, or center, basically. So here, if we take an example of how you fill these in, if you look at the column 1, say time 1 and frequency bin 4 on the right-hand side, you get a value of 7 and a value of center below that. Basically, that just looks to the previous step, says, okay, I could have come from the value of 5 or the value of 3 there, i.e. bins 4 or 3. Which one is more likely? And you can say, okay, this is a larger number. What's the probability of me staying in the safe frequency bin or jumping one? And you can define that. In this case, the probability of staying in the safe frequency bin, or the log probability, sorry, is 1, and the other 2 is 0. So it's more likely to be in the same center bin, which is that 5, plus the data point you're in, which is a 1. Hopefully you might be able to see my mouse there. And it adds up to a 7, basically. And you can repeat this step. So you go to the next time frequency bin, you look back a step, and then you say, okay, where did I come from? So you can look for that cell of time bin 2 and frequency bin 3. It's got a value of 14. It looks up, down, and center. Which one's most likely? It's the center one again. And so you can just repeat this process all the way to the end. And then if you look in the end time step, you just look for the biggest number and say, okay, here it's 22, and then you follow those up, down, and centers backwards. So you end up with a track there, which gives you the maximum sum of power through that, but substantially less calculations than you would if you searched over everything. So it's very efficient. And that's how the Viterbi algorithm works, and we just apply this to gravitational wave data, basically. One of the benefits of this algorithm, which I might not mention as well, is that it doesn't really follow any particular model, and so it can search for any long duration signal over time. So we've had this identify compact binary coalescences as well at some point, although it's not as good at that as other searches, obviously. So what do we get out? Okay, so this is an example of the output of the search. So this top panel is the data, how the detectors. That's a year's worth of data, and it's again about 0.1 hertz wide. And we've simulated a continuous wave signal in that, which is what this red track follows. And that's one of the outputs of the search, is this Viterbi track. So that's a track which gives you the maximum sum of power. So that's one output. It's got this Viterbi statistic, which is the sum of that power along that track. And the third output is this thing we call a Viterbi map, which is the bottom panel. And that was that right-hand image, which you fill with data as you update. But you get these really nice looking plots, which we've also called feather plots in the past. And they're quite useful for various reasons, but you can imagine them as basically, it's related to the probability that there is a signal present in any particular frequency time bin there. They're just quite nice looking plots. So how do we actually do a search? Most of the time we just use the Viterbi statistic. So that is the sum along the track. And we've done plenty of simulations of this where you generate thousands of bands, inject a signal into them. And so here you can see the gray there is a noise band. We don't inject a signal, but run the Viterbi algorithm lots of times and lots of different realizations. And then you can inject a signal of 80 SNR and 100 SNR, basically. And obviously, as you get to higher SNR, it's better at identifying those signals because we've got higher values of the statistic. 80 and 100 SNR might sound really large, but that's over the course of a year spread out. So in any particular FFT, it's usually about less than 1, really, is the SNR that you get. So it's not as big as it sounds. So for the LIGO detectors, we have 2 detectors, right? We don't just have this one thing we want to search through. So we have to adapt the algorithm ever so slightly, but we can also leverage those 2 detectors to improve our search. So if you're expecting an astrophysical signal, you'd expect a similar power in each detector, assuming they're both of similar sensitivity. And if they're wildly different, then that's more likely to be some instrumental artifact, such as instrumental lines, which plague all CW searches, just narrowband, long duration lines. And so we developed another statistic, which basically looks at the power in each of the detectors at any particular time, and says, okay, what's the probability that this is from a signal compared to it being from noise or a line? And so we have this odds ratio now as a statistic. And then we perform the search in the exact same way as I described before. But using this instead of just one power, it's this statistic now. But again, you can see this is an example of it ignoring this narrowband line quite well. But that's a particular kind of line, and there are many, many other kinds of instrumental artifacts. So on the right-hand side here is an example. There's two different ones there of how, even with this addition to the algorithm, we are still sort of plagued by these lines. So that top panel, there's two quite wide lines of at similar frequencies in each detector there as well. So there's not really much you can do about this other than just notch them out. So that's not too much of a problem. But below the lower panel, you can see we follow the edge of a line where there is consistently high power between the two detectors. And the Viterbi really likes that because that's consistent with what we expect from a signal. Now that's not great that we're still finding those. And the other thing which we want to leverage is the fact that it's really obvious by looking at this that that's not likely to be an astrophysical signal, right? Just looking at these spectrograms with your eyes. And so this is where we move on to the next stage of our search, where we wanted to use convolutional neural networks to try and classify each of these spectrograms and outputs of the search. So yeah, so there's three main inputs we wanted. So you just wanted to use a pretty simple CNN, convolutional neural network, using various different inputs and all the information we have to hand. That includes the Viterbi statistic, these Viterbi maps, those feather plots I mentioned, and the two spectrograms from each of the detectors, assuming we're just using two detectors here. Now I say downsampled in this slide because we do actually downsample them because it takes quite a long time to generate this data and to train on. So we wanted to make these as small as possible. So we just downsample them to roughly a sixth of their size. I can explain more about that later. And so what networks do we use? So we have separate ones for each of the data inputs that we have. So the Viterbi map, for example, runs through a couple of convolutional layers and a few fully connected ones to a single output where it can predict a number between 0 and 1 and say, is there a signal present that's close to 1 or not close to 0? And it's basically the same network structure, but it takes in for the spectrograms, but it just takes in the two detectors data instead and tries to classify that as to containing an astrophysical signal or not. I should point out at this point as well that whilst we initially developed, one of the goals of it was initially to find signals which do not have to follow the standard frequency evolution of a continuous wave signal. Here we introduce some sort of model dependency by training on injections that we've made. But how do we combine these together, right? So we've got two separate networks, and we want to combine that information to try and improve our sensitivity. And so what we ended up doing was just chopping off that last layer. There's 8 weights actually on that final layer for each of these two networks. So we just remove all of those, add another 16, I guess, 8 for each, and just join them up to a single output. And then retrain again. So it's sort of a type of transfer learning. And then we just retrain and hope that improved our sensitivity, basically. And we also add in the Viterbi statistic as well there. So there's an extra bit of information. And the combination of all these three is what we hoped would be our most sensitive set. What data do we use to train on this? Because the whole benefit of this was to use real data, right? Because we want to search for instrumental lines. We want to remove the effect or limit the effect of instrumental lines. But we can't train on the same data that we search through because that will bias the network to something it's already seen. And so what we do instead is we break up the real detector data, anything between, I think it's about 40 and 2000 hertz. We break up into alternating bands, which we call even and odd. So these are 0.1 hertz wide bands, and then every other one goes into each other category. And this allows us to train two separate networks then, one on the even bands and one on the odd bands. And then when we go to search or to test the network, we can run the odd bands through the even trained network and vice versa. That way, no network ever sees data that it's tested on or that it searches through. We're also limited in the amount of data that we have. It's a year's observation, it's the entire observation, and we've only got 2000 hertz to play with, really. And so we do another thing where we augment the data to try and increase the number of sort of noise realizations that we have. So we do various things, like on the right-hand side here, you can see an example. There's a big broad line through that as well. But we flip it in frequency, roll the FFTs in time, and flip them in time. And this just gives us, more noise realizations, which we can then duplicate and inject a CW signal into for training. So that's how we generate training data for this, based on real observations. Now this slide, there's a lot going on here, I know, but this is basically the entire pipeline and what happens. So from taking time series data from the detector, creating FFTs, whitening them, and then splitting them into these two categories, where we create training data, train the networks for each of the even and odd bands, and then create test and search data, they're called. Test data has some injections in it. Search data is what we search through, so we don't inject any signals, we're just searching for a signal. And then at the end there, you can see all the lines crossing. That's basically testing on the odd bands with the even data and vice versa. So how did this work in the end? Did it detect anything? Well, it knows the answer, but how we can sort of characterize its sensitivity by doing lots and lots of injections again. So this is using that test data. And here is an example of an efficiency curve, which basically any SNR there says what fraction of the signals did I detect that I injected at any given SNR. Yeah. So on the far right, so basically further to the left is better. I detected a lower SNR signal. And so on the furthest right is the Viterbi statistic on its own, that output before we did any neural networks. And then as we start to introduce them, so just doing the spectrograms on their own without actually using SOAP at all, that part of the search is that orange curve, which improved our sensitivity quite a bit over the SOAP search. But then combinations of SOAP with i.e. the Viterbi statistic, that is, with Viterbi maps and spectrograms can each improve our sensitivity just a small amount. So we managed to push past that and somewhat automate this search. So one of the other benefits of this as well is that the speed that it takes, right? The speed or the time that it takes. So the majority of the time with these is generating training data, so injecting signals and then running the Viterbi search, which for all of our training data, of which we had hundreds of thousands, really, I can't remember the exact number. It took over 200 hours to generate all of that. That's easily parallelizable though, so you can just send that off to lots of CPUs and it'll be done in an hour or so. So that's okay. And training the networks, the maximum was about 9 hours, I think. But most of them were approximately an hour. But once you've trained your network, as soon as you want to test this, as you may already know, it's really fast. It takes a few minutes to load in the data and then a few seconds to actually classify those signals. So it's really quite fast. But including the data generation and the training and everything, even if we run that on a single CPU or GPU, we were still 5,000 to 10,000 times faster than the existing all-sky searches at the time. And we were of a similar sensitivity as well. I should have included a plot here actually, but we achieved a similar sensitivity in one of the mock data challenges that was run, but yeah, substantially faster, which I was quite pleased with. Okay, yeah, so that was that's the search in terms of identifying a signal. But the whole goal of this is to rapidly identify a signal and then say to another search, go and have a look over here for this particular signal we may have found. But all we have at the minute is our 0.1 hertz wide frequency band, and just saying there's something in here, go and have a look. But what we really want to return is some more constraining distributions in the parameter space, i.e. the sky and the frequency. They don't have to search as broader parameter space. Now to do this, we wanted to use the Viterbi track, right? Because that track follows this Doppler curve, and that Doppler curve contains all the information for sky position, frequency, and frequency derivative. So we thought, okay, that'll be the easiest thing to use. The trouble with it is the how you define a likelihood for this. So on the right-hand side here, you can see a high SNR signal on the top, where it closely follows the true frequency evolution. And in the lower plot, you can see it sort of sometimes follows the evolution and randomly wanders off. And the lower plot is the lower SNR signals, which is likely what we're going to find first. So how you define a likelihood for this track is not entirely clear, and we tried many different methods to try and do that, and nothing was particularly successful. So what we moved on to was a likelihood-free methods, and in particular something called a conditional variational autoencoder. Now this is a technique which was initially developed for compact binary coalescence parameter estimation, and we're using it on binary black holes mostly at the moment, and looking to extend that. So this was entitled Vitamin initially, and that was just recently accepted into Nature, and the link's there if you want to read into that anymore. The basic idea of this, I'm not going to go into too much detail, as this is an entire presentation in itself, but the initial idea, the general idea is to minimize the cross entropy between the true posterior distribution of the thing you're trying to estimate and some distribution which the network outputs. And there is a sort of clever little bit of maths, which you can change that into this equation at the bottom here, where you split it into 3 separate distributions, which you can all approximate with a neural network. Can somewhat gloss over this slide, as there's a lot of details in there. But basically, you have 3 networks that you train simultaneously, which take in some combination of the true parameters of the signal which you've injected, the actual data which you've observed, i.e. these Viterbi tracks, and then there's this thing called a latent space in the middle of this as well, which is another thing you predict. But they're all things you can sample from, basically this latent space and the outputs you sample from the distribution. And you run it slightly differently in training and testing. But you can somewhat treat this as a black box, as in you put in data and outputs samples from a posterior distribution. So not that you should necessarily just believe every black box that you see, but you can test it quite a lot. And so one of the ways we did this was to compare it to traditional sampling techniques, things like Markov chain Monte Carlo, MCMC, or nested sampling. And so we could generate these sinusoidal tracks and just add, or just have additive Gaussian noise to that, such that we can compare and we have a likelihood definition then. And here's an example of one of those, where in blue is our conditional variational autoencoders output, and in orange is the MCMC output. And you can see they agree quite well in this example and often do. So yeah, that was a successful test to prove that this does work on nice Gaussian noise, which we understand well. But this isn't the real goal of this. The main goal was to run this on the Viterbi tracks where we couldn't define a likelihood. And so to generate the training data for this, we basically have to generate loads and loads of spectrograms, inject signals, get the Viterbi, run SOAP, get the Viterbi track out. It takes a fair bit of time to generate, despite it being quite quick. And we wanted to run this about 1 million times to get enough training data for this technique. The other difficulty is that we found is that it struggled to identify when the signal was on the track and when it wasn't. So one of the ways we tried to help this is basically to tell it. So during training, you can add information to say the Viterbi track is not near where the true signal track is. And then once you've trained it, you can get it to predict that instead without it knowing that information beforehand. So this version of the algorithm returns the 4 Doppler parameters and also 360 other parameters, which are related to the probability of each track being associated with the true signal or not, and it will predict that for you. So it's 364 it's 360 because there are 360 samples once a day for a year for this. So how does that work? So here's an example of that working quite well, really. So in the top right is the Viterbi track, which you can see as these samples, which are green to red. So green here refers to it thinks that the track is on the signal, on the true signal, and red means it thinks it's not contributing to the true signal, and it uses that information to estimate the parameters. So the corner plot here just shows the posterior distributions, and the truth is well contained within that. But I was quite pleased on the right hand side here how it correctly ignored when the data wandered away from the truth, and we find that it agrees quite well. And then there's further examples of this as well. Here you can see it wanders off because those black lines refer to the edge of our 0.1 hertz widebands. But it successfully gets these correlations and works quite well. And so we have this full pipeline now, which searches for a signal quite rapidly, and can classify the signals using convolutional neural networks as well. And it also has this parameter estimation stage at the end. And when we have this running, it can run this sort of continuously, like on a weekly or monthly basis if we want. It takes on the order of hours to do an entire search once things are trained. They shouldn't take much more training after the initial. You can sort of retrain on new sets of data and things. So yeah, in summary, that's what we've done. There's a problem in the CW world where there's a huge parameter space and a huge amount of data, and was there a lot of semi-coherent techniques around? We just wanted something really fast, and so we did develop that. And then we have these extra machine learning techniques which we use to follow up. So that's sort of all I had to say, I think, on this. If you have any questions, do fire away.